Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid, or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of a fluid? Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as the flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function. In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.
The real explanation all starts with a little mystery. A little story in 1893. There was this warship called the HMS Daring, designed to go super fast. One of the first ever torpedo boat destroyers. It was meant to be one of the fastest warships in the world, reaching up to 27 knots, which I guess is super fast for a 260-ton member of the 19th century British Royal Navy. But when they first tested the Daring, it was nowhere near that speed, and they couldn't figure out why. For all of its 4,200 horsepower, it was a complete failure. No one knew what was wrong until they looked at the propellers, and they found not cracks, not damage, but bubbles. These little bubbles and little clouds of bubbles were forming on the propellers and slowing down the warship. But the propellers were completely submerged underwater. There was no source of air. So if it wasn't air bubbles, then they didn't know what was going on until two engineers, Barnaby and Parsons, discovered the bubbles were a phenomenon called cavitation, which was actually theorized over 100 years earlier by a famous mathematician, Leonard Euler, who came up with this idea that something moving fast through water would, quote, leave a void, like a bubble of nothingness. But cavitation had never been observed before until they were testing this warship. Cavitation happens when fast objects travel through fluids, like this bullet. As the bullet travels through the water, this massive bubble forms and it immediately collapses. It's easier to see though in this video of a bullet going through ballistics gel. When something moves fast through water, it creates an area of low pressure behind it. Just like, you know how a big truck moving on a highway will suck you forward behind it, or how bikers draft behind each other? That's because right behind the vehicle or the bike, there's this area of low pressure that I learned is called a slipstream, which is why you feel sucked forward because of the low pressure. It's the same idea with cavitation. A bullet moving through water quickly will create this area of low pressure behind it. So low that something happens to the water. Actually, I'm gonna show you what happens with a little experiment. You can do this at home with adult supervision. Get some water close to boiling and then pour it into a syringe. Close the syringe off airtight and then pull it, and it'll start to boil. It's vaporizing. The water is turning into a gas because when you decrease the pressure by pulling the syringe, or you could decrease the pressure by taking the water up to a higher altitude where the air is at a lower pressure. And then the phase diagram from your high school chemistry textbook tells you that water will eventually change phase when you change the pressure. It'll vaporize. In fact, if you went up to 60,000 feet and you spit outside, your spit would start to boil, assuming that your saliva is at body temperature. So if your bullet moves fast enough in the water, it'll leave behind an area of low pressure because it's pushing into water ahead of it. So that's creating an area of high pressure in the front and then leaving behind an area of low pressure. Although in some cases it creates low pressure in front. That's a really fun little aside, but typically you get higher pressure in front and lower pressure behind, creating the vapor bubble behind the moving object, which is exactly what the engineers working on the HMS Daring found when they looked at the propellers. When the pressure behind the propeller dropped below 0.46 atmospheres, the water vaporized. But as soon as the propeller slowed down or the bubbles moved away from the propeller, the bubbles would collapse, but super violently. The collapse takes less than 5 milliseconds. It's so violent that they damage metal propellers little by little. The bubbles will even sometimes collapse with so much power they release a flash of light in a process called sonoluminescence. You can see that in the bullet footage. Check it out. Right here, you'll notice these subtle flashes of light as the cavitation bubbles collapse back down. People don't know exactly why the light is produced. There are some theories that involve virtual particles, or that it's a process similar to Hawking radiation, which is the radiation produced at the event horizon of black holes. But don't leave this video and say, black holes are formed behind boat propellers, because that's not what I'm saying. The takeaway here is that we don't fully understand. We don't know yet how sonoluminescence works. It's an open area of research in physics.
An experimentalist who has pioneered another promising cold fusion method, sonocavitation, is Dr. Roger Stringham of First Gate Energies. Using ultrasound frequency, Stringham has observed extraordinarily high temperatures caused by the process of cavitation, where microscopic bubbles in water tunnel their way into target metals. Metals like silver, titanium, palladium, and platinum are melted by intense heat created during the brief moment it takes for a bubble to collapse.
Well, this is a cavitation process going on in the bubble, and the acoustic energy is absorbed by the liquid, and there is a certain point in which it creates small voids which actually grow and then collapse very rapidly. And that is the cavitation idea. The temperatures that are required to create these ejectocytes are at least the melting point of the metal, and it looks like we are actually in the vapor phase, which is gaseous metal, and this amounts to, for the liquid metal, 1600 degrees Kelvin, and for titanium higher. For the vaporous state is several thousand degrees higher than that.
Stringham is seeking to commercialize his device for use as a home power multiplier that can supplement conventional electric power usage.
It's a process called sonoluminescence.
The first time I saw sonoluminescence was in a darkened room. I was transfixed to look at this spherical flask of fluid. And you look into the center, and in the center see a glowing blue-purple light, which could be seen with the unaided eye. It looked like a star in the heavens.
Seth Putterman called it the star in a jar, a tiny spot of bright light contained in a flask of liquid. This star in a jar is made when a sound wave is passed through a small bubble inside a flask of liquid. And this sound wave makes the bubble do something remarkable. First it expands, then it collapses. And this collapse happens so violently that vapor molecules trapped inside the bubble slam together and heat up so much that the bubble gives off an incredible burst of heat and light, several thousand times a second, giving the appearance of a star.
Waves are energy in motion. They carry momentum and information through the universe. They are all around us. Light waves, ocean waves, sound waves, and many others. Sound waves are pressure waves caused by a physical interaction. They move through matter, and in doing so, cause it to vibrate. In this experiment, two techniques are used to visualize sound waves. Water resting in a low-frequency speaker, and salt resting on a high-frequency mechanical wave driver. As the instruments are activated, they vibrate in resonance with the waveform, revealing geometric patterns. The patterns change with the pitch and volume of the sound wave, visualizing the nature and shape of waveforms.